Hi everyone, we are again the solar energy team, or in this case we will continue with the objectives and the project development. For the first topic, that is the simulation of the physical effect, it is necessary to remember that in the solar cells the photovoltaic effect is a derivative of photoelectrical effect. Then, if the sun shines with no cloud disturbance, we will see a perfect behavior as described by the following equation, that is E equal to Planck constant by F, that means frequency. Finally, that is a simple straight line if the weather conditions remain unchanged.
A transducer is a device that has the mission of receive energy of an electrical, mechanical, nature, acoustic, and supply other energy of different nature, but of characteristics dependent on the receive. Therefore, in the case of a photovoltaic cell, there is a change in photon energy or the called energy pockets, and these break the covalent bonds of p-type and p-type semiconductors N, thus producing an electric current.
Next, I will explain how the transducer works, that is, the operation of a photovoltaic cell. Before moving on to the simulation, I will explain the function of each of the blocks that make up the diagram. Let's start with the PS constant block. The PS constant block represents the generation of a physical signal of constant value. In this case, it represents the solar radiation or irradiance, whose value is 1000 watts per square meter because it's the typical irradiance on a clear day. The next block is electrical reference. This block serves to represent an electrical ground connection. All those models that have electrical elements must contain at least one electrical reference block. The next block is voltage source. A solar panel uses a non-regulated voltage source because the current and voltage it provides change depending on the load. And this is also the reason why the solar panel always looks for the maximum power point. The next block is scope. The scope block shows the graphs of the current, power, and voltage generated by the photovoltaic cell. Next block is the current sensor. The current sensor is a device used to measure the flow of current that circulates through the composition of the photovoltaic cell. A current sensor is also called a current transducer or transformer. The yellow rectangle shows some data that will be relevant for our simulation. It is the short circuit current and open circuit voltage, which will be discussed later. The next block is the solve configuration. The importance of the solve configuration block is that each physical network that is represented by a Simscape block diagram requires information from the solver from the simulation. This block specifies the solver parameters that your model needs before the simulation can begin. The next block is the multiplication. The multiplication block is the simulation is used to obtain the power, since according to the formula, the power is obtained by multiplying the voltage and current. The next block is PS Simulink Converter. Its function is to convert a physical signal in Simulink to an output signal. In this case, the output signal corresponds to the current. This block is used to connect the outputs of a physical Simscape network to Simulink oscilloscopes. Then we have the Simulink PS Converter block. The function of the block is to convert the Simulink input into a physical signal, which in this case will be the voltage conversion. This block is used to connect the Simulink blocks or source two inputs on a physical SIMSK network. The next block is the ramp. This block generates a signal that starts at a specific time and value. The parameters pending start time and initial output of the model determine the characteristics of the output signal. Finally, we have the solar cell. This block represents a current source of the solar cell and includes the following components. Number 1. Current induced by solar energy. A solar cell is composed of two resistors in parallel connected to a source and two diodes. Its operation is represented by current equations. The solar cell block can simulate one or more cells connected in series. In that case, the output voltage increases and it is much more efficient than the simulating one by one. Once this has been explained, it should be clarified that for the simulation, the solar cell block is configured with 60 cells, that is like a solar panel. Number 2. Temperature dependence. Temperature is a very important factor since various parameters of the cells depend on it. Internally, the block provides relationships between temperature, current and resistance, which are the parameters that can be modified according to what you want to simulate. Number 3. Predefined parameterization. This pre-parameterization data allows you to configure the block for the representation of components from specific providers. Number 4. Thermal port. This is a highly parameterized by default, but in general it's used for modeling thermal heating to the solar irradiation. Now the simulation will start with a time of 60 seconds. Once the program is complete, the scope will show us the characteristic curves of a solar cell. The first one is the voltage intensity curve. As we can see, when the voltage between the cell's terminals is low, the current intensity remains constant and at a higher voltage. The current decreases rapidly. In the image, we can see a representation of what the solar panel will be. In the voltage current curve, there are two important points that we mentioned above. The first is the green point that corresponds to the short circuit intensity, which is defined as the intensity of a dipole in a time interval where the voltage is zero. The image on the left shows you the representation of what the short circuit will be inside the panel. The next important point is the open circuit voltage, which corresponds to the orange point on the graph. Open circuit voltage is the maximum voltage available from a solar cell that occurs when the current is zero. It corresponds to the amount of forward polarization on the solar cell due to the polarization of the solar cell junction with the current generated by light. According to the data established in the simulation, we have an open circuit voltage of 0.6 volts. But remember that this value is only for a single cell. Therefore, if we want to obtain the total open circuit voltage of 60 cells, a simple multiplication is performed. The open circuit voltage of 60 cells is equal to 0.6 volts per cell multiplied by 16, which gives us a value of 36 volts. The following graph is the voltage which can be obtained if a resistor is at between the terminals of the panel circuit, as shown in the image. As we can see, it is a straight line whose slope can be obtained by Ohm's law. Depending on the value of the resistance placed, the slope of the line will be either larger, low resistance, or smaller, high resistance. The last graph is the power graph, where the highlight is the maximum power or nominal power. It is determined by measuring the electrical current and the voltage in a circuit, while varying the resistance under precisely defined conditions. This power is related to the efficiency with which the cell transforms solar energy into electrical energy. For a common silicon solar cell like the one we are working, the efficiency is given by an approximate value of 17%. In general, the characteristics curves of the solar cell are represented in this way, but the voltage, current, and the power graph are together, as we all see the points of the short circuit current intensity and the open circuit voltage.
Transducer quantify light, making it possible for machine and electrical installation to distinguish between light and the dark environments. The conversion of light into an electrical signal can be carried out, for example, by photoresistor (LDR) light-dependent resistor. With increasing light, the electrical resistance decreases. In addition, you can use semiconductors that, if light level change, certain electrical properties will also vary. The electronics connected to the sensor will have the task of linearizing the signal if necessary and converting it into a standard signal. Light transducers are used where it is necessary to activate an artificial light source when daylight intensity decreases. Light transducers capture the light intensity and convert it into an electrical signal where a controller can work on the measured values. If you connect with a data logger, you can store the brightness value over the period of time, allowing, for example, to determine the hours of sunlight.
In this part we have a representation of how energy is transformed until it reaches a home. This diagram can help us to answer the following question.
Hybrid solar thermal and photovoltaic technology achieves the simulating production of heat and thermal energy from solar radiation, has a higher energy efficiency when adding to equipment to the fundamental advantage of system compared to energy production through photovoltaic system and separate thermal lists in the reduction of the physical space required, as well as the possibility is using common support structures. Currently, there are several prototypes. The experimental validation of the results obtained in the different simulations must have a test facility that allow simulating the different operation conditions to the which system will be subject. This type of installation will allow to measure both the thermal and photovoltaic production of different prototypes, being able to vary the most influential parameters for the performance, such as the flow of circulating fluid, the impulsion temperature, and the inclination of panel. With this, the aim is to be able to test the different prototypes in different scenarios.
It's necessary to adapt a rectifier circuit of the energy captured for use in the room? To answer this question, we must observe and think about what the specific movements occurred just after the energy is generated electricity. As we have mentioned, the photons that are irradiated by the sun and the collide with the semiconductors of material, it translates into direct current. Therefore, if a rectifier is needed to drive the energy to a room in the case of cells photovoltaics. Well, we reached the end of this presentation. We hope the explanation was good, and thank you very much for your attention.